Yeah. So good morning to everyone. I welcome you all another presentation on control system subject. In the subject we are looking after the time domain specifications of second order control system. So in our previous presentations we have seen what are the time domain specifications of a second order system. Basically we have seen there are five important specifications are there, starting from the first one is delay time t suffix d, and the second one is the rise time t suffix r, and the third one is tp means peak time, and then the fourth one is maximum peak overshoot, and then the fifth one is the settling time. And for these five types of specifications we have seen the respective mathematical expressions. So in especially in competitive examinations you need to remember these formulas, and directly the problem will be given on these specifications. Okay, so why I explained with their proof is that you must able to know it how they have been derived. So in this presentation just I would like to solve one of the important exercise problem that has been asked in one of the topmost competitive examinations in India is UPSC IAS. It is asked in UPSC IAS 1999. Okay, by the way you can see it is the lecture number is 34. Today's presentation will 34. So let us see one important example on these time domain specifications. So the problem is given like this. The response C of t, okay, the response C of t of a system is described system is described by the differential equation by the differential equation. So the equation is given like this. It is d square by dt square of C of t plus 4 times d by dt of C of t plus it is 5 into C of t equal to 0. This is the given differential equation. Basically it is d square, the second order derivative is there, differentiation or derivative is there, hence it is called a second order system because d square is the highest derivative. D square by dt square, the second term is a d by dt. This is the first order, this is the second order. Then you are asking that what kind of system is this? Is it the question is like this. There are four options are given. One is it undamped? Is it undamped? Second is it underdamped? Underdamped. And the third option is critically damped. Critically damped. And the fourth one is oscillatory. These are the four options given. So this particular question is asked in UPSC IAS in 1999. They have asked. they have asked. So this is the system they have given in the form of differential equation, and you are asking that find out, is it damped or under damped, critically damped, or what kind of system is this? So for this, what we have to do, so it is simply you have to apply the Laplace transformation for this. It is a second order system. So okay, from that you just compare this particular equation with the standard definition of a second order system. Okay, I will solve for this, and we know that the solution. So we know that this is, what is the second order system? In general, for any second order system, the response or the transfer function, not the response. What is the transfer function normally? The transfer function is nothing but your C of S by R of S is equal to, what is this? Omega n square by S square plus 2 times zeta omega n times S plus omega n square. This is the transfer function of any second order control system. Okay. Here, if you equate the denominator part, S square plus 2 zeta omega n S plus omega n square, this is the denominator part. If you equate this equal to 0, then this is called a characteristic equation. Okay. So what is the given equation here? What is your differential equation then? It is d square by dt square of C of t plus 4 times d by dt of C of t plus 5 into C of t equal to 0. So this particular equation you have to compare with this denominator part. Okay, means that you simply apply the transfer function, I mean Laplace transformation here. Then upon the application of the Laplace transformation, the second order derivative comes like this. It is simply S square plus C of S plus, it is 4 times S into C of S plus 5 into C of S equal to 0. And just you consider this part. This is nothing but, if you take C of S as common from here, from this, take C of S as common here. If you take C of S as common out, then what you will have? S square plus then 4S plus 5 equal to 0. Consider this part only. Consider that part, S square plus 4S plus 5 equal to 0. Now this particular equation, you have to compare this particular equation with the standard form. What is our standard form? And again, in the standard form of transfer function, you have to consider the denominator part only. What is the denominator part? S square plus 2 times zeta omega n into S plus omega n square. This is the denominator part. You need to compare this particular with this equation. Then S square, for S square is there, and for S coefficient 2 zeta omega n is equal to your 4. This implies, upon equating these two, 2 zeta omega n is equal to S coefficient. So here this much equal to 4. So from this, so what is omega n here? From this you can write zeta value. Zeta is equal to 4 by 2 times omega n. So 2 ones are 2 twos are. So it is 2 by omega n. Clear? Then what is omega n value? From here, so omega n square is equal to 5. Omega n square is equal to 5. So what is omega n? Root 5. Radians per second normally. It is radians per second. Root 5 is nothing but, obviously, what is the value? It is approximately, it is 2.23 root 5 value. Then substitute this omega n value here, zeta. So then zeta is equal to 2 by 2.23. Then this value becomes 0.894. What is this? It is less than 1. No? This value is, zeta value is 0.894. So your zeta value is less than 1. Means, so this comes under underdamped category. So from the option given, what are the second option? Underdamped is there, no? That's why this particular system comes under underdamped system. The given response belongs to underdamped system. Okay. Likewise, we have to see. Therefore, you need to remember, you need to exercise, you need to practice more examples so that you will enjoy this. Okay. So we'll stop this presentation here, and in next presentation we will see some more examples based on this time domain specifications. Okay. Thank you. Have a good day.